for me to introduce to you as today's speaker, Amelia Stockholm. So Amalie is a PhD student in the ISIMBA group at Aarhus University under the supervision of Victor Aguirre Gerson-Koch. And within this group, Amalie has, among other things, been heavily involved in developing the BASTA stellar modeling code that I'm sure many of you know about. And early in her PhD, Amalie led the very detailed astroseismic study of a Kepler subgiant, which also included a careful benchmarking against the radii expected from or measured from interferometric studies. Since then, Amalie has expanded her analysis to the galaxy as a whole in a galactic archaeology, or maybe rather galactic paleontology study of the Milky Way using a carefully selected cohort of red giant stars and including a lot of information from Gaia also. So this is the work we will hear about today from Amalie. So please, Amalie, the floor is yours.
Thank you, Nick. Can you see my slides? Good. Yeah, well, thank you all for being here. And thank you to the organizers for arranging this Good Vibration series and for giving me the opportunity to share some ongoing work with all of you. Yeah, again, my name is Amelia Stockholm, and I am a PhD student at the Stellar Astrophysics Center in Aarhus at Aarhus University. And I'm a student of Victor Silva Aguirre, or Victor Aguirre Gerson-Koch, and I'm part of his research group, ISIMBA, where we are investigating stars using Bayesian statistics. I am finishing my PhD this summer, and what I will present here today is work that I've been doing for this last part of my PhD, which I'm currently finishing up, and I hope to get on the archive within a few months. Yeah, and just to give you basically my project up front is that I have about almost 22,000 stars with astroseismic, kinematic, and spectroscopic data, which I am investigating to find signatures of evolutionary processes that have happened in the Milky Way past. I'm also going to be honest with you that this is not a finished paper with finished conclusions yet, so I hope that is all okay, and I hope that I can present some of the conclusions with you on archive in a few months. So let's just jump right into it. So this is a picture taken or made by the Hubble telescope, and all of these points in this picture are different galaxies. One of the fundamental problems in astrophysics today is our lack of understanding of how galaxies form and evolve over time. Our current understanding of the formation of structure in the universe begins at the Big Bang, and it successfully explains the large-scale properties of the universe. However, the formation and evolution of the individual galaxies remain to be fully understood. We can observe this whole zoo of different galaxies, covering a wide range of shapes and sizes and colors, and we know that they must evolve over the course of cosmic time. So any complete theory of physics must be able to explain the diversity of the observed galaxies, as well as why there are fundamental similarities between them. Here we have a nice artist impression of our own home galaxy, the Milky Way. The Milky Way is at the same time both generic and unique. It seems to be a generic disk-type galaxy with structural components that are similar to those of other disk galaxies in the local universe. On the left here, we see the face-on view, which shows us the spiral structure in the galactic disk, where the majority of the stars, about 75% of them, are located into spheres with a diffuse mixture of gas and cosmic dust. On the right, over here, I don't know if you can see my mouse, we have this edge-on view of the galaxy, where we can see that the galactic disk is a disk. It's relatively flat, close to the galactic midplane. In both of these, we can see that we have our sun that is placed right here. It is placed very close to the midplane of the galaxy within the galactic disk at a distance of about 8 kiloparsec away from the galactic center. We can also see that we have this galactic bulge in here, which in the central portion of the Milky Way, which glows a bit more red and which also extends to higher distances above the plane that the disk does. Another component that is present here is this roughly spherical structure with a large radius, which is the halo, and this contains some isolated stars as well as many globular clusters. Overall, the Milky Way has somewhere between 10 and 100 billion stars, and its structural components are similar to those in other disk galaxies in the local universe. This indicates that the mechanisms that have shaped the Milky Way might be universal. The Milky Way is also a unique cosmological laboratory, as it is the only galaxy that we can see, that we can study up close and from within. This is a stellar density map from the Gaia mission, which shows us the distributions of stars on the night sky. Brighter region here indicates higher concentrations of stars. And besides this being an amazing achievement, this also nicely shows some of the structures that we saw in the Aarhus impression just before. We can see this is in galactic coordinates. So we see this is the disk here. We see some bulge structure in the middle. We see some of these dust lanes and stuff in the disk. And if we look above or below this plane, we can look into the halo. This also very nicely highlights one of the challenges by studying the Milky Way, namely how difficult it is to get a good overview of the galaxy when we are positioned within it. All other galaxies we view from the outside, and many of the primary components can easily be identified. But because we are positioned within the Milky Way disk, and because our view is obscured by dust and gas and stellar densities when we're looking for the disk, the big picture can be hard to see when we are only seeing some of the puzzle pieces. However, this is also our big advantage because the Milky Way is the only galaxy where we can resolve the individual stars that make up all of these galactic substructures. In other galaxies, we have to study the integrated stellar distributions, but here we can actually study the individual stars and get a much closer look at it. So stars are formed throughout the lifetime of the Milky Way, and they carry signatures of the conditions in their birth environment and of their subsequent history. We know that the Milky Way was born a few million years after the Big Bang, and that it has been shaped by different physical processes during its life. These processes leave a unique imprint in the stars. The stars can retain a fossil record of the environment in which they were born and of signatures of events that have impacted them until the present day. We can therefore use the stars as time capsules and use them to reconstruct the history of the Milky Way. This way we can learn about important processes in the Milky Way's past, and we can, by learning about our galaxy, we can also help understand the in situ formation of external galaxies where the individual stars cannot be resolved and where this kind of study is impossible. So this is basically the ultimate goal of this field of research. It is to learn about the galaxy by learning about its stars. So if you want to infer the Milky Way past, what are the key diagnostics that we can measure? These are the chemical compositions of the stars, stellar orbits, and their ages in particular, along with some of the other physical parameters, of course. Using these measurements in combinations with models and simulations, we can study the history of the Milky Way, and we can hope to answer questions like what processes set the present structure of the Milky Way, what has happened at what time in the Milky Way's past, and how many major merger events have the Milky Way been through, and are there any merger events currently ongoing? I will briefly go through these stellar measurements so we are all on the same page. So first we have the chemical abundances. And very simply said, the surface abundances of stars can be measured by directing their light into or through a spectrograph, which separates the wavelengths present and measures the relative amount of radiation at each wavelength. Using models of stellar atmospheres and atomic physics, these spectra can then be converted into relative elemental abundances and also a measure of other stellar properties, such as the line of sight or radial velocity of the star. Different elements have different formation channels. You have probably seen a figure like this before, which provides some kind of overview of different channels, formation channels of different elements. At Big Bang nucleosynthesis, which in this figure is marked as this blue color, only the very lightest elements were produced. Everything else has been produced in later processes. We know that low mass stars, they can live longer than the age of the universe, and hence some of them will have formed at very early times, and they have survived until the present day. And in their atmosphere, they have a fossil record of the environment in which they were born, as that surface, as their chemical composition reflects the interstellar medium in which they were formed. So if we know the processes and we know the rates at which these processes occur, then we can produce chemical clocks, or we can use abundances as an indicator for where and when the stars were born. And I'm going to go through one type of chemical clock or enrichment process. And well, by going through some of the enrichment processes in the Milky Way. And we know that supernovae is a large contributor to the chemical enrichment of the interstellar medium in the galactic disk, of which generations of stars are born. And here I just have two types of supernovae. I have supernovae type 2 and supernovae type 1a. And we know that supernovae type 2 are the core collapse supernovae. They have, increasingly heavier elements are generated by fusion in the stellar core. And the more massive a star is, the higher up the chain it can go, all the way up to iron. After iron, there's no longer energy to be gained by fusion, which means that there is nothing to hold the gravitational collapse of the star, which then causes the star to collapse, rebounds, and explode, ejecting all of its envelope containing processed material and therefore enriching its local interstellar medium. This kind of process is very rich in the so-called alpha elements, so elements that consist of a number of alpha particles or helium-4 cores. We also have supernovae type 1a, and they are thought to be either mergers of two white dwarfs or the explosion of one white dwarf that has accreted material from a companion star and then exceeds the Chandrasekhar mass limit. And in this kind of explosion, a huge amount of iron peak elements are ejected into the interstellar medium. So putting this together, we get most of our alpha elements from core collapse supernovae and most of the iron peak elements from type 1a supernovae. We also know that type 2 supernovae were the final stages of very massive stars that live fast and die young. Type 1a supernovae consist of the final stages of lower mass stars, which fuse nuclei at a slower pace and therefore live longer. So in the early days of the Milky Way, we know that the chemical composition was very poor in metals. So the first generation of massive stars, they die relatively quickly and they enrich their surrounding material. And we also know that there has to be a delay between these two types of formation channels, because the very massive core collapse or the massive stars that produces type 2 supernovae, well, they can happen at almost instantly when a generation of stars are born, while type 1a supernovae, well, first we have to wait at least 1 gigayear for stars at 3 solar masses to maybe have reached the state of a white dwarf, and then we also need these white dwarfs to either have companions or to merge, and then we will start to have these type 1a supernovae shortly thereafter. So we know that there is a delay between the two. So when we are then plotting the alpha over iron ratio as a function of iron over hydrogen, we can see that there must be some kind of time variation on the galaxy as a whole. And then only when these type 1a supernovae start to kick in, then we will get this kind of decrease in this ratio all the way down to the present day. This is, so basically, a star's position in this type of diagram contains a clue about the age of the star or when it was born. And this is one type of chemical clock, but of course others do exist as well. Let us move on to stellar orbits. And again, very simply said, the orbits of the stars can be constrained using measurements of their movements along with a model of the gravitational potential of the Milky Way. Due to the motion of the Earth around the Sun, then it looks like all of the stars are moving in small circles, and the size of the circle is inversely proportional to the distance between us and the star. This is what is called parallax. Stars also move around in the galaxy, and the projected motion of this movement is what we call proper motion, and it is basically a vector on the night sky. So putting these two kinds of motion together, I hope that you can see the video now. This is a very nice video made by the Gaia team. But then we can see how we have this circular motion, which combined with the proper motion vector produces this spiral pattern. This is what Gaia observes, and then they measure the spiral pattern and then extracts celestial positions, proper motions, and parallax of the star from the model. If we then add a measure of the line of sight velocity from spectroscopy, then we have the full 6-dimensional information needed to convert all of these projected motions into the 3-dimensional velocity space. Oh, there we go. Orbits also change over time. The disk of the Milky Way contains giant molecular clouds. It contains structures such as bar and spiral arms, and these structures produce a time-varying potential that induces the stars to scatter and to change orbits. So they kick the star in velocity space, they apply some torques, they exchange angular momentum, and all of these perturbations over time can affect the stellar orbits and causing them to heat up. So down here in red, I have an orbit of a young star that is born in a disk and is moving in a basically perfectly circular orbit. But then due to all of these perturbations, it gets pulled and pushed a bit, and then this kind of orbit can change. It can change eccentricity, it can move out, it can move inward, it can move in different ways. And the star's radial and vertical motion will therefore increase and not just move around in the galactic disk, but also in some of the other directions. This also means that if we are looking at the velocity dispersions of different stellar populations, we would expect the velocity dispersion to increase as a function of stellar age. We also have different processes at play because there are also mergers, galaxy mergers. If a galaxy is torn apart by the tidal forces of a larger system, then the stripped stars will continue to follow similar trajectory of their progenitor system. So if, for instance, the Milky Way halo is the result of mergers of many different objects, then the star should define some streams that wraps around the whole galaxy. Here I have a video, I hope that it runs. This is from the simulation of the Gaia Enceladus merger. So the blue stars here is showing a nascent Milky Way, and the red star is the dwarf galaxy that is getting merged with the Milky Way system. And you can see how the red stars, they still keep some of their kinematic signatures. They do not blend in with all of the blue stars and follow their patterns. They still keep some of the information that they come from a separate system. So if a star was born in a different place than the Milky Way, then their dynamical patterns should be different from the stars that were born here. Oh no, there we go. And the last of these key parameters is age. And age is a fundamental parameter to this field of research because it allows us to piece together this information in the right chronological order. I've gone through how the chemical and the kinematic signatures should change as a function of stellar age. But because we have a mixture of many different processes happening at the same time and everything, then precise stellar ages is the key to actually disentangling all of this, so we can figure out what has happened at what scale in the Milky Way. There are many different ways of determining ages, but one of the methods is, surprise, surprise, asteroseismology. Asteroseismology is the study of starquakes or stellar pulsations, and in solar-like oscillators, the pulsations are excited and damped by the near-surface convection layer, which produces these stable oscillations, standing waves. And these standing waves inside the star is directly related to the physical properties, such as the temperature and the density of the stellar gas itself. And therefore, the pattern of pulsations depend profoundly on the structure in the stellar interior. This is what I've tried to show over here, where we see at least a schematic of some oscillations that could happen within a solar-like oscillator. Well, we also have some genus, but when we are then, so how do we measure this? Well, again, very simply said, we can detect these oscillations by measuring the resulting subtle changes in either the brightness of the star or the radial velocity or line of sight velocity of the star. And then we will get something like this time series over here. As we are working with repeating patterns, then we can perform a Fourier transform on the time series data, which will result in a power spectrum, where we should see something like a cone-like pattern for these solar-like oscillators. So something along these lines. So if the resolution and frequency space is high enough, then we should be able to resolve these individual frequencies. But we also, we have these, we can also reconstruct or decompose this pattern into two global asteroseismic parameters, because there seems to be some kind of envelope with a Gaussian-Lorentzian shape. And one of the global asteroseismic parameters is the maximum of this envelope, what we call nu max, or frequency of maximum power. We also have these very regularly spaced frequencies. And here we have the other global asteroseismic parameter, namely delta nu, or the large frequency splitting, which is the spacing between consecutive modes of the same angular degree. As the star evolves, then the frequency pattern changes, because the cavities where these standing waves inhabit, they change. Here we have this very, very nice figure from the Extent Review in 2013, where we have a main sequence star up here in navy blue, and then we have more and more evolved stars all the way down here to a red giant star. So we have this nice evolutionary track here. And we can see how the frequency pattern changes. We can see that the pattern becomes more condensed or more compact as the star evolves. And we can also see that the peak, the envelope, the maximum, also moves towards lower frequencies. So in terms of these two global asteroseismic parameters, as the star evolves, we see that delta nu decreases and nu max also decreases. Including these asteroseismic signals in the age determination of the star greatly constrains the inferred ages and allow for a much more precise age determination. So now I have gone through these key diagnostics: chemical composition, orbits, and age. And in general, this field of astronomy has been on the rise for the last couple of years due to the revolution in the sheer amount of data available. We have these huge spectroscopic surveys, such as Apogee, Galar, Lamos, Rave, and so on, which are just increasing the sky coverage and observing stars in multiple wavelengths and bands. We have Gaia, which measures distances and celestial motions to an unprecedented level of precision, of micro-arcsecond precision. And then for asteroseismology, we've had the amazing Kepler mission, which had a deep look in the same patch on the sky for 4 years. Then we had the Renaissance mission, K2, which looked in many different directions and really helped us find asteroseismic targets in different regions of the Milky Way. And now we have the amazing TESS missions, which takes this a step further and really scans huge parts of the sky in a rigorous manner, and which will aid the field of galactic archaeology even further. So this is all very exciting, and if you like to work on huge data sets, then you're in for a treat. So let's just breathe, and now let us have a look to what I've been spending the last part of my PhD project looking into. So again, on this figure, we have the Gaia density map in the background, and I have overplotted my sample of stars, and you can see that we have many different, you can see that I have a Kepler field and that I have stars from different K2 campaigns. I also have two very navy blue regions here for the Corot fields. And overall, I have about almost 22,000 stars when I have pruned the data and taken a selection function into account. All stars in this study are evolved low mass stars, either hydrogen shell burning red giant stars or helium core burning red clump stars. And these stars are ideal as they are relatively common and intrinsically bright, allowing us to study a representative sample of the stellar population at a great range of distances from the sun. And here I have like a summary slide of what my sample consists of. So 21,706. They all have delta nu and max from either Kepler, K2, or Corot. It is the excellent group of people behind the K2 GAP project, which has provided the most astroseismic quantities for this sample. All of these stars have 5-dimensional astrometric quantities from Gaia DR2. Unfortunately, no one spectroscopic survey has observed all of the stars because I have stars on both the northern and the southern hemisphere. But well, I'm using data from Apogee Data Release 16, the value-adding catalog of spectroscopic properties for Lamos DR5 and Galar DR3. And all of these stars have JH and K magnitudes from 2MASS. So something that really should be easy, but always gets a bit confusing and maybe goes a bit wrong when you're working with a big sample of stars, is cross-matching different catalogs. You run into memory issues or handling issues as different surveys use different type formats or fill values or whatnot, or the columns are switched in Simbad or something else. I wrote a Python program that I call SkyCats, which makes all of this a lot easier, and also it makes it a lot easier to keep track of different columns, different column types, and if you want to have a common renaming scheme, then that is also allowed. And this will be available on GitLab when the paper for this project lands on archive. So be on the lookout for that. Yeah, so now I have my set of observables and I want to derive stellar properties such as mass, radius, and age. And as Mikkel already mentioned in my presentation, I have been working with BASTA. BASTA, or the Bayesian stellar algorithm, is an excellent software that is developed in our research group, and I'm part of the BASTA developers team. And basically the idea behind BASTA is to create the most versatile pipeline for stellar property determination. BASTA in its current form is fast and it's flexible. It can fit observables from spectroscopy, photometry, astrometry, asteroseismology, and predict stellar properties based on these given constraints. It can fit everything that we predict from our stellar models. So if you, for instance, have a radius from interferometry or a bolometric luminosity from fitting spectral energy distributions, BASTA can also add that. BASTA is designed for the space-based era where hundreds of thousands of stars are fitted and where not all of them have the same data or quality of data available. And again, let's just go through Bayesian inference just briefly, because that is what BASTA is based on. So what this means is that we have some data here, and we compute the probability of the data based on the likelihood of observing the data based on our stellar models. We can also take prior knowledge into account. Like for my study, I took an initial mass function into account, which describes that it is more likely to observe a low mass star than a higher mass star, given their different number density in the galaxy. All of this is combined using Bayes' rule or Bayes' theorem, and then BASTA outputs the posterior probability. So BASTA calculates the joint probability density function from the given input parameters, with desired weights or priors or whatever you want to give it, and then Basta returns this full posterior probability and also reports stuff like median and percentiles and standardized visual output to make it easier to evaluate and interpret the results. And because I'm adding the astroseismic quantities delta nu and nu max, this in particular narrows down the likely parameter space and therefore the uncertainties in age. And here I have tried and made a comparison to a different study, the Sanders and Das isochrone ages from 2018. For this sample, Sanders and Das 2018 did not have the ages for about 13,000 of the stars. But for the stars where they actually do have the ages, I have made this histogram. So Sanders and Das is the orange one and Basta is the blue one. And here the median fractional uncertainty in age for the Sanders and Das distribution here is about 35%, while the median value for the Basta results is about half of that. It's about 18%. And this just highlights what we gain in precision when we are adding astroseismology when deriving ages. So what do we actually see? Well, if we separate the sample into bins, so this is a bit basic plot, I'm sorry for that, but like I've separated the sample into different bins, spatial bins. So down here I have stars that are close to the galactic midplane. Up here I have stars that are 1 to 2 kiloparsec away from the galactic midplane, and up here it's 2 to 3. And then here I have the stars that are closest to galactic center, and then going outward, we're going out towards the outer edge of the galaxy. In all of these bins, what I have is I'm plotting age and I'm plotting the alpha over iron ratio on the y-axis. And if we're looking at the solar annulus, where I'm having the most stars because they are the ones that are closest to us, we can see that we have a peak at the younger ages and at a solar alpha iron ratio of about 0. If we are going towards the inner part of the galaxy, we can see how we don't really have anything down here. The peak is moving up towards higher values of alpha. Whereas if we are moving out towards the outer part of the galaxy, then we basically have not that many stars up here at higher alpha values, but more stars down here closer to 0. If we are moving up from the galactic midplane, we also see that this peak is at a higher alpha value, and we also see that it is at older ages in general. So why is that? Well, this is because the disk have multiple components, or said in a different way, that different stellar populations dominate in different spatial bins of the galaxy, something that we historically have been calling the thin and the thick disk, because in stellar counts, you could see that there was an overdensity close to the galactic midplane and something at higher heights above the galactic midplane. In this study, as we saw before, we saw that there was a difference also in chemistry, that one had a higher alpha over iron ratio than the other. And in this study from 2018, astroseismic data was used to nicely demonstrate that there also was an age difference between what they call the high alpha sequence and the low alpha sequence, which is nicely illustrated in this age diagram here. However, with this age difference, you might also expect that the old high alpha sequence were kinematically hotter than the younger alpha 4 sequence, or that the younger alpha 4 sequence had similar velocities to that of the sun. But the authors found that this was not as clear cut. Like if you did a selection in chemistry, then you get something that is a bit more muddy in kinematic space and vice versa. So here, the criteria in this study for whether the star belonged to one group or the other depended on the information available in either chemical space or, in this case, heliocentric velocity space. When you look at this, you can also wonder, is there a way to separate all of this using all of the available information, like finding stars that consistently behave like each other in both velocity and abundance space? And this is what I've been working on for this project. I'm using a clustering algorithm to help me investigate this. And I'm combining information for many more dimensions than was done in the 2018 study. There exist a lot of different algorithms for clustering. An algorithm that performs the clustering needs a set of points, and it needs to figure out, sometimes it also needs to know how many clusters you expect it to find. It also needs a way of measuring the distance between the points, so it can evaluate whether or not it should be in one or the other group. And typically one would use Euclidean distance, but in this case, for instance, like this, you need to be a bit careful because these dimensions have different scales, different units. So that means that if you just blindly ask the computer to compute the distances between these points, then it will behave as if a distance of 1 kilometer per second over here is the same as the distance in chemistry space of 1 dex, which might not be what you want, or the weighting between the dimensions that you're looking for. And for this very simple schematic, like, you also need to, it also depends on whether you are looking for 1 cluster or 2 clusters or 3 clusters, as is here, or maybe 20 smaller clusters. So you also need to find a way of determining how many clusters you're actually looking for. And then you need to also know which dimensions to include. Earlier, I talked about these stellar quantities: chemical composition, orbits, and age. And I wanted to include all of this information in my choice of clustering. For the chemical composition, I just included the iron and the alpha abundances, because we've already seen how that probed the chemical enrichment of the galactic history. For orbits, one could use the velocities, but as you know from Kepler's laws, then velocity changes depending on where on the orbit the star is. Like a star that is closer to its center of attraction moves the fastest, while it moves the slowest when it is the furthest away from its center of attraction. So that, combined with the fact that we have many different stars with different eccentricities and guiding radii, that can wash out some of the structure in velocity space, or maybe it could produce some patterns that are just there by coincidence and basically producing ghosts in the pattern that we're not really looking for. So instead, a different and maybe more convenient choice could be to work in a different coordinate system, namely the action angle coordinates. In an axisymmetric gravitational potential, we have 3 actions, JR, J phi, and Jz, so basically 1 action per direction. And these actions are integrals of motion. And in contrast to the coordinates in position and velocity space, actions are constant over time, at least it is potential. So one way of understanding the physical meaning behind these actions is to have a look at the epicycle approximation of orbits. So this is what I've tried to draw over here. So in the epicycle approximation, an orbit can be approximated as the retrograde motion of this smaller circle, the epicycle, on top of this bigger circle down here, which has a radius that is the guiding radii, or the mean distance between the star and the galactic center over the course of the orbit. The equations for the different actions are given over here. And in general, the action is equal to the line integral over the conjugate momenta over the generalized coordinates. So in this case, it's r, phi, and z. In this example, where we have the axisymmetric potential, then the action in the azimuthal direction, so around, is actually equal to the z component of the angular momentum, which we know is a preserved quantity because there are no forces acting upon the orbit in that direction. So in other words, I guess you could think of this J phi or Lz to determine the size of this blue orbit here. And then we have these 2 other actions, and they kind of defines the size of this smaller epicycle circle. So JR up here basically determines how much the star oscillates around this midpoint in the radial direction. And if I had drawn this from edge on, then we would also have Jz, which determines how much it oscillates in the z direction. So working with these actions is a good way to disentangle the different processes at play in the Milky Way, because they stay more or less constant compared with the velocities. And they have this intuitively physical meanings, at least. So this is a very convenient choice, and these are the ones I will use to describe the orbits from I will use them in my clustering to describe the orbits. And the last property here is age, and here I'm going to use the ages derived by Basta using astroseismic constraints. So now I've set up the clustering. I have these 5 dimensions. I am using a Gaussian mixture model with different components and a full covariance matrix. And now I just need to divide my sample into different subgroups. And this is where I am at the moment. I have done a lot of tests, and if you would like to know more, please ask me about it. But this is where what I'm finding at the moment. This is still work in progress, and this is not the ground truth. Like, it's not like this clustering algorithm can tell me exactly what is the underlying truth, but I'm using this to at least help me figure out what is behaving similarly in these 5 dimensions. So here I'm showing 2 plots because they resemble some plots I've shown earlier in this talk. Here I have the iron and the alpha ratio, and here I have the H-metallicity relation. And I'm finding these 5 components. I have this green, forest green component here, which looks a lot like the traditional thin disk stars or low alpha sequence. It is very young, like you can see that over here. It's very young. It's dynamically cold, moves a lot just in a circular orbit. And it's alpha normal or alpha poor, whatever you would call it. It has a mean age of 4.5 gigayears and just moves more or less like the sun. Then we have these navy stars in the background. I don't think you can see them a lot. There's actually 5,000 navy points. They look a lot like the traditional thick disk stars in all spaces. Then we have the the tomato red stars, which kinematically behave a lot like the thin disk stars, but chemically, as you can see up here, like they extend all the way up to something that we would normally call thick disk stars, or like the high alpha sequence. And I'm trying to figure out exactly if I should interpret this as the overlap between the 2 different groups or as a group on its own. We also have these cornflower blue stars down here and here. These are the metal core end of the thick disk stars, but their orbits is much, much more closely related to the more chaotic moving halo stars. And at least a good portion of these stars can be associated to the splash stars, being splash stars. So basically stars that have been born in the Milky Way protodisk prior to a massive accretion event, which dramatically altered their orbits. So those I'm also looking a lot into, because they could actually have a very nice interpretation if that is actually what they are. And then we have the sand-colored stars over here, and these are mostly the halo stars. I also have some stars over here that look a bit like outliers, but mostly it's halo stars. And with Gaia DR2, multiple new remnants of mergers that have happened in the Milky Way's past have been studied. And I have several stars that are in different regions of interest that I'm looking into, because maybe I could provide some age constraints to some of these merger events. So with that, I have a summary of my work so far. So this is the takeaway message. The Milky Way is at the same time both generic and unique, because it seems to be a typical spiral galaxy, but something happened. Because it seems to be a typical spiral galaxy, but it is the only galaxy where we can resolve the individual stars instead of the integrated light from multiple stellar populations. This means that if we study our Milky Way and learn about the formation and evolutionary processes in its past, then we can apply this knowledge to in situ galaxy formation and evolution in other galaxies. Stars can be used as fossil records or time capsules because their chemical compositions contain information about their birth environment and of their subsequent evolution. Their orbits can tell us something about past galaxy-wide perturbations caused by either structural components or major merger events. And their ages are key to combining all of this into a coherent timeline for the evolution of the galaxy. I have a sample of 21,700 stars with median fractional age uncertainties of about 20%, orbital parameters and spectroscopic properties. And I am using clustering algorithms to aid me separate them into clusters of similar properties and to look for, in order to look for clues and of processes that have happened in the Milky Way past. And there is substructure that we still need to map and explain, and especially when adding the age dimension, which has never been done on this scale before. I am still investigating, but I'm hopeful that I can find and quantify key signatures in the age domain that will help us understand the evolution of the Milky Way. And with that, I think I'll say thank you so much for your attention, and I'm ready to try and answer some of your questions.
Thank you so much, Amelia, for a very nice presentation of your work. I think that Don Kurtz has a question for you. Don, do you want to ask it yourself?
Yes, thank you for that talk, Amalie. In your next to last slide, there was just a very slight decrease with age of the iron to hydrogen ratio, and I don't understand why that should happen.
In this slide?
Yeah.
You say that there is a slight decrease in...
There's a slight slope on that in the direction of decreasing iron with age.
Decreasing iron with age. I don't really see a lot of slope. Like, it might be very slight. So in general, I think in order to understand this space a bit more, because something that is like, we would expect that there is some kind of relation between metallicity and age, right? And we would expect, yeah. And we can't really see that a lot in the space because we're looking in so many different regions of the galaxy. So we're probing many different galactocentric radii and different stellar populations. So one thing that I want to do with this is also I want to basically do this based on position in the galaxy, and hopefully I can try and get because some of this will be washed out due to radial migration. So if I'm using some of the orbital information that I have, maybe we can try and actually figure out how much it is washed out, and we can try and actually probe the space a bit better.
Okay, thank you.
Thank you.
I think we have a question from Mark on the chat, and then I'll take. I don't know who was first between Daniel and Tim, but they will figure out.
Okay.
So Mark.
Thanks. Yes. Yeah. Thanks for the talk. This is some really interesting stuff. I was just wondering with the Gaussian mixture model how you account for the effects of uncertainty, particularly with the age, because we get some large uncertainty sometimes with a bunch of stars.
Yeah, that is a very good question. So what I've done so far is, so again, I didn't know how to do this, but the way that I would usually work with this kind of multiple, multimodal distribution is that I will take the different distributions, I will separate it, I will basically sample it in different quantiles, and then I'll run it, make all of the pairs, and run it through all of this. So how can I explain this a bit better? So for each star, I have an age. I have an age probability distribution. I can use this because I know where the mode is, and that's very nice. I also know where the different quantiles is. So if I, for instance, say that I have the 10, 20, 30, like 10 different quantiles, I can then pair them up with different quantiles in some of the other dimensional spaces. So in action, with action and with metallicity, I need to assume a Gaussian, but still. And then when I have all of these pairs in all 5 dimensions, I can run this through and then I can get an estimate of uncertainty. This is not great computationally, but I at least haven't found any other way of us trying to solve this issue.
So is it equivalent somewhat to sampling from a distribution and finding how frequently it falls within the same cluster?
Like, it is similar, but there is a big pitfall when you are sampling from multivariate distributions, namely that it is very, very rare for you to have pairs that are in the tails in all of your distributions. Like, getting that pair that is in the tail of both of your 5 different spaces, that will happen very, very rarely. You need to have a lot of samples in order for that to happen, like many, many more than people might think. So in order to do, so if you're doing all of this in quantiles and actually making a conscious decision of actually sampling the full distribution, then you are certain that that is what you will get. You can then weigh each of your pairs by the likelihood and the different probabilities. And this way you will be sure that you have these tail distributions, like I have a mental Gaussian here. Like, then you are sure to have the tails of all of your distributions, and you can then weigh the points by the likelihood of given by the distribution. I think a different way of saying it is when you're sampling from a multivariate distribution, you're basically drawing small points of equal weight from your distribution. And what I'm suggesting is that instead you are drawing in a pattern throughout your full distribution, which you know, and then you are weighing them. You're changing the size of the balls, or however your analogy is, by what the value of the probability distribution function is.
Thank
So
you.
this way, I'm more sure of the uncertainties than if I was just sampling it.
So Daniel or Tim, I think you had a question.
Can you hear me?
Yes,
Yeah.
it's a bit loud, maybe too loud.
Is this better?
Yes.
Yes.
Okay, I have a couple of questions. Do you have plots showing your different clusters in terms of the JR, JZ, and LZ parameters?
In this talk I only have these two
Okay.
that are in. So here I have the action diamond. I don't know what is the real name for this plot. So here I have LZ down here. So this is basically, if we recall, this is a measure of how big the orbit is, and here I have JZ minus JR, and I have divided all of this by the total, the sum of all the actions. So this goes from 1 to -1 in both directions. In this space, I would expect all the thin disk stars to basically be a small point over here. This is a plot that people are using a lot when you are studying the halo, because this really like meshes out the entire halo over here. Then you have thick disk stars that go a bit further, then you have all of these halo stars. And like, I think here. So for instance, in the Myung 2019 paper, they identify that these stars down here should be part of the Gaia Enceladus galaxy, at least sometime in the past. And these stars over here might be what is called the Sequoia stars. And I have some stars, at least in some of these bins. This is not necessarily the plots that you were looking for, and I'm sorry, but like this, I think this is the best plots I can show here.
Okay, well, that's already very good. And my second question is perhaps a bit naive, but I was just wondering to which of the 5 clusters the sun belongs.
The sun belongs to the green one. but that is a good test at least to see. So, and these according to this, it belongs to what we would call the thin disk.
Okay, thanks.
So Connie just reminded me in her post on the chat that we should encourage young researchers to ask their questions, and I'll try to give them priority. So one of the juniors, we have Tim Bedding here, who wants to ask a question.
Well, I agree with Connie, but since I already have my hand up, thank you for a wonderful talk. My question is what we can expect from TESS. For example, if you go back to your plot where you had all of the panels of the galaxy with alpha versus age, how far out will TESS actually go? Because it's only really looking in more in the local neighborhood.
Oh, do I have that? I don't have the plot. TESS, some people that are really into TESS, please correct me if I'm wrong here, but like, I think TESS has a complete volume up to, is it 3 kiloparsec away from the sun? Like it has some volume where we should expect to find all of the targets. So at least these quantities here should be filled out a bit more. This is also where I have the most stars. Like I'm trying to correct for a selection function, but that is always difficult to do. So like I'm also not sure what, like I should in principle be able to draw some conclusions from these stars down here, but I'm not trusting my results enough to do that, I think. But I think with TESS we should be able to at least probe a lot more stars in these 3 kiloparsec. Thank you, Victor. Yeah, so it was a 3 kiloparsec volume away from the sun with giants. So these middle panels should be populated very well with TESS. I hope that answers your question.
It does, thanks.
So another young researcher with us here today, Connie, wants to ask a question.
Well, I was just thank you, Amalie, for a wonderful talk. And on this beautiful plot on your screen, that triggered my question on how many different stellar evolution model type input physics are in BASTA. Do you use them all? And, you know, they give elongated uncertainty, as you have already alluded to. It's annoying, you have to work with percentiles, but that's better than just pretending as if everything is white Gaussian. So yeah. Did you, what kind of different input physics did you consider?
Yeah, so for this, I've been using the BASTI isochrones. I'm not, and maybe I should, I'm using a fixed value of mass loss. Like I should maybe have expanded this a bit more, but I'm using the full BASTI isochrones. Something you might notice on this plot, like goes up all of the way to 20 gigayears, which is like, this is something that we're doing in order to not make some artifacts in our data, because if we are forcing our data to be on a much smaller thing, then you can basically you can screw up your distributions. Yeah. So in BASTA, some of the observables, we only know the mean value and a standard deviation, so we are assuming them as Gaussians. For the parallax, which I'm using, so for BASTA, in this case, I'm fitting metallicity and temperature along with delta neo max, which I'm also using as Gaussians. I'm adding phase as information because that is available for most of my sample, also thanks to Asteroseismology. And then I'm fitting parallax. So that is a combined measure, of course, of parallax, you need to take the dust map into account. So it's a function of the position on the sky. You also have your apparent magnitude that you need to find. And then there's this whole transformation, because you can't assume that a parallax distribution is Gaussian, because we know that the inverse of the parallax is a Gaussian, right? But we know that distance should be Gaussian, but that is not the case with parallax. So I'm combining all of this in VESTA, and then we get the outputted probability distributions. I'm then using the outputted distributions for parallax. That is what I'm using when I'm doing the orbital calculations, so that those at least are consistent. But it is annoying, and it is difficult to make comparisons when you have asymmetric error bars and probability distributions. Like for instance here, where Sanders and Das are using symmetric error bars, and I'm using, like I have distribution, so I need to, in order to get a fractional uncertainty in age, I need to convert or approximate what my symmetric uncertainty would be. I don't know if all of this answered your question, but like we're trying to do this and actually taking the probabilities into, or the distributions into account, but it is difficult, and at some point you need to just have some approximations.
Yeah, sure. So you're trying to solve the universe as a whole. Maybe my question would filter down to, what if you weren't use the BASTA isochrones but other ones? I think that's something you could answer, and would couple to the transformation of between luminosities and parallaxes in practice. So because you are using isochrones, right? You rely on them.
Yeah.
So, assuming that they are correct in your method. And I think that might be a little bit too optimistic. That's just what I'm saying, okay?
Yeah.
So assessing that before you come in front of your jury might be a useful exercise. Thank you, Amalie.
Thank you.
So I had Mikkel writing me a direct message asking me the floor. So it was just before Victor. So Mikkel, if you want to ask your question, and then Victor.
Sorry, I just couldn't figure out how to raise my hand in this. Maybe it's because I'm the host, but yeah, that's how it goes. First of all, thanks, Amalie, for the great talk. I was just wondering, now that you have all these age estimates, while it's not really the approach you're taking, have you considered trying something similar to the studies by Bovey et al., for instance, where they use monoabundance populations as age proxies, and then look at vertical and radial scales, for instance, to test inside out, upside down formation, looking at vertex deviations and so on for different bins in age to test these formation scenarios.
That is what I'm doing. I'm trying to study the gradients in the vertical scale and in the radial scale, and trying to do that both in age and in spatial, like trying to investigate that. But I don't have a lot of things to show there yet.
I'm sure it will come. Thanks.
So we'll have to wait for the nice paper to come for the big conclusions. So Jörn, so Victor, actually you lowered your hand, so I think you can ask.
No, just a very brief comment regarding to what Connie asked. You're absolutely right, and this is something we need to test further. I mean, there's a lot of input physics that we don't know. All these stars have different alpha abundances. We're assuming our isochrones only have one set. There's overshoot, there's mass loss, all the nasty things that you know. And that is a complete study that is a bit beyond of the scope what Amelia is doing. On the other hand, we have the PDFs of the ages, and we are assuming that within the uncertainties on the ages, these shifts should be included. So as a first start, I think that's what, that's the assumption. Doesn't have to be true, of course, and that needs to be tested, but it's a place to start.
And then Jörn for the last question. Please.
Well, thank you very much. Thank you for a really great talk. I'm learning a lot about galaxy evolution now. I also like your comment that the galaxy is both generic and unique. That's something you can apply to each one of us, actually. But so my point really is one thing that you're not including in your characteristics of the stars is where they are in the galaxy and their position in the galaxy. And of course, they're moving about. So and we're just seeing a fairly local sample of them, but there could be information about stars being close to each other, for instance.
Yeah, so being close to each other. So actually, So I am including position in a way that I'm trying to study some of the gradients and something like these dissection plots where I'm dividing them into different spatial bins. But as I think I have a bit of a confusing movie. I don't know if it's, but as you maybe can see here, so what I have up here is position of stars in Z and X and Y and X. And then I have different stars that, maybe if I go one back and one forward, like they start together as one clump and then we allow them to evolve, and not that much, by only 1 gigayear. In action space, which is down here, they stay more or less constant. But in positional space, they can spread out very easily, just due to them being in different orbits that have different orbital parameters. So I'm not including position per se in, for instance, the clustering algorithm, because that kind of information is kind of already included in the action. And if I'm including that in position, then I will bias the results. I don't think that is the approach to use for field stars. Yeah,
okay. So that makes sense. And the actions are clearly very interesting. And of course, it's nice to see Epicycles coming back after being sort of kicked out of the solar system. So
it's yeah.
Right, thank you.
So thank you very much, Amalie, for a very nice talk, and thank you all the youngsters for your nice questions. I think it's something that we should keep in mind, to have more young colleagues to take part actively in these seminars. I would just like to remind you that you can find the videos of the past seminars if you were not able to attend on the website. You will find the website link on the announcement emails that you must have received. Please encourage your PhD students to contact us and to try to get a seminar with us. All the details can be found on the website. Well, I think it's time for me to let you go. So thank you so much for being here with us. Thank you again, Amelia, for your talk, and Mikkel for the nice introduction. And please, if you're a member of the steering committee, you can stay with us a little longer. Bye, everyone. Thank you.